start new topic, motion in plane. So we will try to cover these three topics here: motion in plane with constant acceleration, and then uh, relative motion in two dimension. So let's start with motion in plane, and here we should start with position vector and displacement. So let's say a particle is moving in plane. Let's say this is the path on which a particle is moving. So let's say it is at point P1, and then from there it comes to point P2. So we are considering its motion between these 2 points. And as this motion is in two dimension, we should take a reference frame which has two axes. So this is y axis and this is x axis, and unit vector along y axis is j cap, and unit vector along x axis is I cap. And let's say this is origin, and let's say at point P1 its coordinate is x1, y1, and point P2 it is x2, y2. So position vector for point P1 will be this one. Let's say this is vector r1, and position vector for point P2 will be this one. Let's say this is r2. And now if we draw a vector from point P1 to point P2, this vector will be the difference of R2 and vector R2 and vector R1, and we call it displacement vector. So if we are drawing a vector from point P1 to P2, and let's say this is delta R, then delta R is displacement vector, and this displacement vector can be given as R2 delta R vector. So this is given as R2 vector minus R1 vector. And now R2 vector can be written in its components, which is x2 I cap plus y2 j cap, and R1 can be written as x1 I cap plus y1 j cap. We have done this thing in previous videos. We can rearrange these terms and write x2 minus x1 I cap plus y2 minus y1 j cap, and further we can write delta r vector or displacement vector. This thing we can write delta x, and this thing, and of course I cap here, and this thing we can write delta y and j cap. So this is displacement vector. And now if at point P1, when the particle is at point P1, let's say the time is t1, and when it reaches point P2, the time is t2. So the time duration or time interval of journey delta t can be given as t2 minus t1. So this is time taken. Delta t is time taken to move from point P1 to point P2. Now we can go on and write expression for velocity. So velocity will be displacement divided by time. So this will be delta x divided by delta t, or we can write delta r here, delta x I cap plus delta y j cap divided by delta t, or we can write separately delta x by delta t I cap plus delta y by delta t j cap, and in short we can write v equals to, this is x component of velocity vector, and this is y component of velocity vector. Means uh, what is the velocity along y axis, and this is the magnitude of the velocity along x axis. So this way we can get velocity vector, and this velocity is for the entire journey from point P1 to point P2. So this velocity is nothing but average velocity to be instantaneous velocity. So let's say, so if from here to here the time interval is delta t, so we can reduce this time interval and we will move back to point t1. If we are making this time interval tending to 0, it means we are nearly at this point, point p1. So instantaneous velocity at point p1, we can write delta r vector divided by delta t vector. Still it is average velocity, but if we add this limiting factor, here we can write limit delta t tends to 0. That is, we are moving closer to this point p1. And then whatever velocity we will get here, this velocity will be instantaneous velocity at point p1. And we can write this thing we can write in short notation dr by dt. That is time derivative of position vectors. So what is happening here? If position vector for point p1 is r1, then velocity at point p1 will be b r1 by dt. So we will continue using this general notation dr by dt, and let's write this position vector into components, and then we will have v equals to b. Instead of r, we can write x I cap plus y j cap for position vector. Let's say this is point P and position vector for this point P is r. So let's say this is r, vector r, and this component is x and this component is, let's say, y. So we can write as unit vector along this is I cap, and here unit vector along this axis is j cap. We can write vector r equals to x I cap plus y j cap. So we are using the same thing here, and then by dt, and we can write dx by dt I cap plus dy by dt j cap, and then we can write vx. This thing is the component of instantaneous velocity along x-axis, and this thing is component of instantaneous velocity along y-axis. So this way we can write this instantaneous velocity in terms of its components, and then we can go for magnitude. So magnitude of this thing will be under root vx square plus vy square, and of course in vector notation there is here 2 vx vy and cos theta. But what is happening here? The theta is 90 degree between I cap and j cap. So ultimately this term will be 0. So no need to write it. So this is velocity, magnitude of the velocity, and then we can get direction also. How can we get direction? We can write tan theta equals to vx by vy by vx. This way we can get tan theta. Let's say, how can we get it? Let's say this is x component of velocity vector, and this is y component of velocity vector at any point, let's say this point P. So this will be the resultant velocity vector, and of course this should be Vy. So this is 90 degree, and we are talking about this theta. So here theta is the angle made by resultant velocity vector with the x-axis or the component along x-axis. So we can write tan theta equals to Vy by Vx. Let me make it more clear. Yes. So this is Vy by Vx. And now let's move to the topic acceleration. So what is acceleration? It is a rate of change of velocity, we can say. So let's say at point P1 velocity is V1, and at point P2 velocity is V2. So the acceleration will be V2 minus V1 divided by time interval. This is acceleration. And if we are taking in general, Let's say this is velocity, and this is change in velocity, and then this is change in time. So this will be acceleration. And if we are taking limit delta t tends to 0, we will get another way of acceleration. So now you can easily identify that this acceleration is average acceleration, and this acceleration is instantaneous acceleration, which we can write dv by dt. And of course, you can extend the argument. You can just write this thing into its components, and then you can get acceleration along x-axis and y-axis. Means the component of acceleration along x-axis and y-axis. The same thing can be done here also. This will be delta v vector divided by delta t only. And of course, we can just write it into its component, and then we can get the components of average acceleration along x-axis and y-axis. So the same argument can be applied here as we have done in case of velocity. There, for entire motion, if we are considering a single velocity, then that velocity will be average velocity. And if at any instant of time we are taking the velocity of the particle in motion, that velocity will be instantaneous velocity. In the same way, here we can apply the uh, concept of average acceleration for entire journey and instantaneous acceleration at any particular point of time during the journey. And one more thing, if P1 at point P1 velocity, initial velocity is V1, and at point P2 the final velocity is V2. So one more thing, we can write here average velocity can be written as the final velocity plus initial velocity by 2. Okay. Let me summarize the things we have discussed today. So we have discussed about position vector, and then displacement. Displacement is also a vector quantity. And then we went for velocity, where there is average velocity and there is instantaneous velocity. And then we discussed about acceleration, the same way, average acceleration and instantaneous acceleration. So in case of average velocity, this is displacement vector by time, and for instantaneous velocity, it was dr by dt. In the same way, average acceleration, so let's say acceleration av was change in velocity by time interval, and instantaneous acceleration, which we simply write as without writing here any subscript, this is dv by dt. Of course, we can split these things into their components, whether it is change in position vector or displacement vector here, or position vector here, or velocity vector here, or velocity vector here. We can split into components to get component wise velocities or accelerations. So, and one more thing I can add here, this acceleration, which is dv by dt, we can write d of dt, and velocity is already first derivative of position, time derivative, first time derivative of position vector. So we can write acceleration as d square r by dt square. So remaining thing we are going to discuss in next class.